Hello again. In this video lecture, I would like to continue the designing of the combinational circuits. Suppose that we have two bits and we want to add these two bits with together and find their results. So in the case of the two bits, as you can see, we can have four different possible combination. Suppose that if we have two bits, we called one of them as x, another one as y. So we say that we have four possible combination for the x, y as 2-bit 0, 0, 0, 1, 1, 0, and 1, 1. So these x and y are our input. So we want to add these two bits with together, then find the result. So in the result, as an input, we have the sum as s and also carry. So we know that when we want to add these two bits with together, we can have the carry. So now x, which is equal to 0, 0 plus 0, the summation is 0 and the carry is equal to 0. 0 plus 1 is equal to 1 with the carry of the 0, and 1 plus 0 also is equal to 1 with the carry of 0. 1 plus 1 will be equal to 2, which is equal to 0, 1. So in the sum section, I write 0, and for carry, I write 1. So as the design procedure that we talked about that in the previous lecture, we said that after finding the number of the input and output, in this case both of them are true, then we assign the symbol for the input and output. We do it. So we uh, assign x, y for input and assign the c and s for the output and find the relationship between input and output. Now it is time to find the Boolean function for each of the output of system. So you can see that we have two outputs, C and S. Now using the K-map also you can do it, but if you look at to this column of C and the column of S, you can see that if you look at to the column of C, this C is the output of the AND gate. You can see that when one of the input is 0, the output is 0. When both of them is 1, the output is 1. It means that the C is the AND of X and Y. So it means that I can directly find the output Boolean function of C, which is equal to x and y. Similarly, if we look at to the column of S, you can see that here, when we have 0, 0, we have 0. When we have 1, 1, we have 0. And when the x and y, one of them is 0, another one is 1, the output is 1. So means that the S or this column is the output of the XOR gate. So we can say that C is equal to X and Y and S is equal to X or Y. So using this concept, we can write the C as this function, and also we can write the S as x prime y or x y prime, or in this form. Now we can also implement this circuit. You can see that here we have x prime y, and or both of them to find the C. And for the case of the C, we can use the AND gate, or we can directly use the XOR and AND for the actually sum and carry of the two addition of 2 bits. We called this circuit as half adder. The meaning of the half adder is addition of 2 bits. So if we have 3 bits, how we can add these 3 bits with together. So we say that in the case of the adding of the 3 bits, something like that, suppose that we have A0, B0, and suppose that we have C0. Okay, now if we add these 2 bits with together, these 3 bits with together, we will have S0 and also C, for example, 0. It doesn't matter. Actually, because we called both of them is C, it is not suitable. Let's call this one as, it doesn't matter, I don't know, D0. Now, I want to design a circuit to do this one for us. Again, if you look at here, you can see that we have 3 variables as inputs and also 2 variables for the output. Okay, for the output. So I can assign the variables for each of the inputs and output. Let's call this one as X, Y, Z. And again, this one as C and S. So at the end, I will have a system that has 3 inputs and output which has 2 outputs. In this system, 3 inputs will be added with together. Okay, now we say that because we have 3 inputs, we will have 8 possible combination. And again, we have to add these 3 bits with together. 0 and 0, 0 plus 0 plus 0 is 0 with the carry of 1. 0, 0, 1 is 1 with the carry of 0. 0, 1, 0 is 1, 0. 0, 1, 1. It means that 0 plus 1 is 1. 1 plus 1 again is equal to 2, which is equal to 0 and 1. 0 for sum, 1 for carry. Similarly, for all of them, you can find the output of the system. So 1 or 1 plus 1 is 2, 2 plus 1 is 3. The binary of the 3 is 1, 1. You can see that we can write it. Now it is time of finding the Boolean function for C and Boolean function for S. Now you can see that with looking at to this truss table, we cannot find it. So it means that we have to use the Carnot map. We have 3 bits. If we draw the Carnot map of the 3 variables for the S, we can find the Boolean function. How? We say that everywhere we have 1, write the corresponding min term as 1 into the Carnot map. This is the 1, 2, 4, 7. You can see that 1, 2, 4, 7. Now we have to group it. You can see that just one of all of the ones separately can be grouped. So if I want to write all of the terms of each groups of 1, for this one is X, Y prime, Z prime, X, Y prime, Z prime. For this one is X, Y, Z, X, Y, Z. For this one is X prime, Y prime, Z. And for this one is X prime, Y, Z prime, X prime, Y, Z prime. So for the C also we can do the same thing. We can say that for the C, as you can see here, we start from the 3, 5, 6, 7. If we write all of the ones, we can see that we will have 3 groups, 2 by 2. We actually make a group. So for this one, we will have x. You can see that xz. For these two, we have xy. For these two, we have yz. Okay, so after finding the Boolean function, we can draw the corresponding actually digital circuit of the C and S. Now we called this type of the circuit as full adder. Full adder. Why we called it as full adder? Because we said that we have adding 3 bits. If we have add 2 bits with together, we will have half adder. If we add 3 bits with together, we will have full adder. Okay, now you can see that here we have too many gates. We used too many gates for producing and implementing the full adder. Now I want to redraw the full adder in another form to show you that we can use the we can implement the full adder using the half adder. So how we can do it? Let's look at here. In this slide, I show you that S is equal to x prime y prime z plus x prime y z prime plus the x y prime z prime plus x y z. If we write the Boolean function of x or of 3 variables, something like that, x or y, x or z, so which is equal to x or y x or z will be equal to yz prime plus y prime z. Again, if we suppose that, for example, this is equal to a, so we have x or a, we will have x prime a plus x a prime. We write same thing, x y z prime plus y prime z prime plus x prime y z prime plus y prime z. Now, if you expand this expression, you can see that we will have x prime y prime z or x prime y z prime or x y z. Now, if you compare this expression with the expression of the sum, you will see that both of them are the same. Look at here and this one, you can see that both of them are the same. So what does it mean? It means that I can rewrite the S in the form of x or y, x or z. Okay, now what about the C? What can I say for the C? Now let's rewrite this C, the Boolean function of this C, in the form of the mean term. All of the ones can be written as the form of the mean term. Now let's write again the truth table of this full adder, and I will explain you how we can do it. Okay, now if you look at here, what is the corresponding mean term of this one? Consider this one. Look at here, the corresponding mean term is x prime yz. Let's write C as x prime y z. Or now, what is the corresponding mean term of this one? Is x y prime z, x y prime z. What about this one? is x, y, z prime. X, y, z prime. What about this one? X, y, z. Okay, now let's simplify this Boolean function. You can see that the z here and here is common. So I can write that z x prime y or x y prime. On the other hand here, xy and xy are common. So I can write xy z prime or z. Okay, now you can see that z prime or z is equal to 1, and also x prime y or xy prime is the x or y. So as a result, I can rewrite again the c in the form of z x or y or x y. So this is the c, and we write the s, we actually rewrite the s in the form of x or y, x or z. Why do I write the actually c and s in this form? Because I want to redraw this circuit. Look at here, we say that we have x and y and also z. Okay, now I want to produce the s. For the s, we say that x or, here is x or y, then this one will be XORed with the z. So as a result, here is s. So what about the c? x or y is AND with z. It means that here is x or y, and here is z. Now we AND. Then we have xy. This is x. This is y. And so at the end, these two ORed with together to find the c. Okay, so excellent. Now look at here. Here you can see that we have one XOR, one AND. Also here we have another XOR and AND. So if you remember, we called one XOR, one AND as half adder and also half adder. What's happening? I could redraw the full adder. So this is the full adder. Get here, from here up to here is full adder. I could redraw the and produce the full adder using two half adder. And here you can see the complete circuit of the full adder.